Okay, hello everyone. So let's start for today's class. Okay, before that we had seen various types of DC amplifiers, and we had seen the basic DC amplifier, that was a two-stage amplifier. Then special DC amplifiers. In this category we saw Darlington emitter follower and the cascade amplifier. Okay, now we will see the DC amplifier with stabilization. Okay, so let us see what is stabilization. What do we mean by stabilization in the circuit? Because stabilization or stable circuit is desired. Okay, we want the performance of a circuit to be stable. It should not deviate with time or temperature or with other parameters. Okay, and in DC amplifiers it is to difficult to maintain stability. Okay, it is difficult uh, to maintain stability. But anyhow, we will have to make the operation as stable as possible, and the variation in output current of first stage gets amplified by second stage. Okay, so this is the problem. This is one of the problem, that if we have multiple stages, if we have, let's say this is the first stage and this is the second stage, first second stage, okay, input output like this. Okay, then anything, we know that the output of first stage is connected to the input of second stage, right? So anything, any signal that's coming from the output of first stage will get amplified by the second stage. Okay, be it signal or noise, anything. Okay, so second stage signal, second stage amplifier will amplify the signal coming from the output of first stage. Also it will amplify any drift or any noise that's coming from the first stage output. Okay, so it will not differentiate between the signals and the noise that is coming from the first stage. It will just amplify that particular thing. Okay, and hence the whatever problem that was fed from the first stage gets even more amplified, okay, by the second stage. So this is one issue when we use multiple cascading of stages. Okay, so and also one of the factors to use limited number of stages. Okay, because of this issue we cannot we cannot use a large number of stages as desired. Okay, so the number of stages gets limited, okay, in the case of DC amplifiers. And for a basic DC amplifier, if delta IC1, if delta IC1 is the change in IC1 due to temperature. Okay, uh, if, if you remember the basic DC amplifier, we had two stages. The first stage was common emitter amplifier, again the second stage was also common emitter amplifier. Okay, so these two stages were connected back to back to form a basic DC amplifier. Okay, so if delta IC1 is the change in IC1, okay, due to temperature, then IC2T, IC1 is for first stage, okay, 2 will denote the second stage current. Okay, so IC in the second stage will be given by AI2 dot into delta IC1 plus delta IC2. Okay, and we know that this delta IC1 is feeding, is coming as input current to the next stage, so it will get multiplied, it will get amplified by the second stage amplification factor, which is AI2. Okay, and plus its own output current, okay, delta IC2. Okay, so this is the IC variation in second stage. Okay, and this is the amplified version of the signal that's coming from the first stage. Okay, So we can write delta IC2T as equal to AI2, the amplification factor, multiplied by S1 into delta ICBO1 plus S2 into delta ICBO2, because we can express IC in terms of ICBO, okay, and IC2 in terms of ICBO2 by this relation, by using this relation, okay, where where S1 is the parameter, that is the ratio between IC1, delta IC1 by delta ICBO1, and S2 is defined by the ratio between delta IC2 by delta ICBO2, okay, where this delta ICBO or ICB, or we know that this is the leakage current, okay, ICBO2 is the leakage current in second stage, and IC1 is the collector current in first stage, IC2 is the collector current in second stage, okay, and note that this delta will denote the change or variation in these parameters, okay. So this is actually the change in IC1 with respect to the change in ICBO2. That is how a change in ICBO1 is going to affect IC1, at how much change in ICBO1 will cause a change in IC1, okay. Similarly, S2 is a ratio that defines that for per unit change in ICBO2, how much is the change in IC2, okay. And uh, these S1 and S2 parameters are the stability factors, okay. These are called as stability factors, okay. That is the change in ICBO with respect to temperature is applicable uh, same for both transistors, okay. So assuming that the both of the transistors that are used in basic DC amplifiers are identical, so we can write that delta ICBO1 equals to delta ICBO2, okay. So overall we can write that ST becomes equal to delta IC2T by ICBO, okay, which can be further expressed as AI2 into S1 plus S2, okay. So finally we can write ST, the overall stability factor, as AI2 amplification factor of second stage into S1, okay, plus S2. This is again similar to this equation. If you can relate this equation to this one, look at this one, this equation, okay, and this equation. So here the overall current was the amplified version of the first current plus the second current, the second stage current, okay. Similarly here the overall stability factor is the amplified version of the first stability factor, first stage stability factor, plus second stage stability factor, okay. All right. So stability in DC amplifier is more complex as S1 gets multiplied by gain of second stage, okay. So as we introduce more number of stages, then correspondingly more number of terms will get introduced here in this equation also, and the first stage stability factor will get multiplied by the current gain of all the succeeding amplification factor of succeeding stages, okay. So this will come like this, okay. So it means that the variation of IC is cumulative. Look at here, the variation of IC is cumulative, okay. Look at this equation or this equation, okay. Cumulative means each for each stage whatever variation is there in IC1 or IC2 or any previous stages, all those variations from the previous stages gets amplified by the corresponding next stages amplification factors, okay. So final IC2, the final variation in IC would be the cumulative of all the previous stages ICs plus the last stage IC. Okay, it means that all stages will be contributing in the final value of IC2 or IC. Okay, the final value of IC. Since this is a two-stage basic DC amplifier, so that's why it is IC2. So the point here is that the IC is cumulative in nature. Okay, for with each stage the value of IC is getting amplified. Okay, so if there is any undesired variation also there, that will also get amplified. Okay, so for the figure, that was the basic DC amplifier. If I can draw the it was something like this. Oh, let me show you that thing. Okay, DC amplifier. Slide. Let me show you the diagram for the basic DC amplifier that with which we had actually started. Okay. Okay, look at this. This was the basic DC amplifier. Okay, and this was the first stage, the common emitter amplifier. Okay, and look at here, this is IC1, okay, which is acting as the input current to the next stage. Okay, and this second stage, which is again a common emitter amplifier. Okay, so remember this diagram. Okay, then for that figure, the value of the equation for S1 is given by actually 1 by 1 plus H21. Okay, where these H denote the corresponding H parameter, and this thing also we had seen in the previous classes. And S2 will be again 1 by 1 plus H21 for the second stage, and AI2, the current gain for second stage, given by HFE by 1 plus HOE into RI2. Okay, where HFE and HOE are the H parameter variable H parameters coming from H parameter equations, and RI2 is the input impedance of the second stage. Okay, so in terms of H parameter, we can write that ST will come out to be HFE by 1 plus HOE into RI2 whole bracket into 1 by 1 plus H21 plus 1 by 1 plus H21. Okay, so this is the equation for a two-stage overall stability factor. Okay, and we want the stability to be we want a more stable circuit, so we want stability to increase. Okay, and one of the ways to improve stability is by adding series and shunt stabilization resistors. Okay, so look at here, this is again that same DC amplifier, where this is the first stage. Okay, this is the second stage transistor. Okay, and here what they have done is they have added some extra resistors, R1, R2, R3, R4. Okay, so R4, not R4 actually, it should be R4 to R7. Okay, so just make a change here, R4, R5, R6 and R7. Okay, so these are the extra resistors that are being added into this DC amplifier circuit. So is the location R4, R4, R5, R6 and R7. Okay, and when you modify this basic DC amplifier by adding these extra resistors, and when you calculate the stability for this particular circuit, and when you compare the stability factor for this modified circuit with respect to the previous circuit, you will find that the this circuit behaves better in terms of stability. Okay, and the reason behind its uh, better performance is the addition of these four resistors, and one factor that is causing this circuit to be more stable uh, is that these resistors are, look at this, this is R4, this is connected in the emitter part. Okay, this is R5 again connected at the emitter. So from the previous subjects, analog electronics and basic electronics, we can say that, okay, we know that the resistors connected in the emitter part are very important, very critical to the performance, basically in terms of stability. So they help us in making the circuit more stable, the resistors which are connected in the emitter branch. Okay, and why is it so? That because they form a feedback. Okay, that they form a feedback between the output and the input. So they form a feedback between the output terminals and the input terminals. Okay, and similarly this R6 and R7, they are also forming a feedback. Okay, uh, again there is one modification that should be there. Okay, this branch is not connected here, rather this should be connected here. So take a note of this diagram. Okay, so R4 and R5, R6 and R7 are forming feedback, giving us the advantage of feedback, and because of this feedback effect, the stabilization of this DC amplifier gets improved. Okay, now there are two types of feedback, we know this. Okay, there are two types of feedback, positive and negative feedback. Okay, so positive feedback and negative feedback. Okay, and we know that which particular kind of feedback is used for making circuit more stable. This one, negative feedback. So this makes circuit more stable. Okay, at the same time it also reduces the gain is reduced. Okay, whereas positive feedback will increase the gain, we know this thing, but also at the same time it makes circuit more unstable. Okay, so our goal was to make the circuit more stable, and hence negative feedback was used here in the circuit. Okay, so this is just one of the method, one of the simple method to increase the stability of the circuits. So look at here, what is the cost, what is the extra elements that is added here? Just four resistors. Okay, and resistors are very cheap, they come very cheap in the market. So it will not increase the overall cost of the circuit much. Okay, it is not going to increase the cost very high. At the same time it will give us advantage of increased stability. Okay, there are various other techniques also, but this is one of the simplest technique. Okay, okay, so let us start the next topic, which is another kind of DC amplifiers. These are chopper stabilized DC amplifiers. So here another concept is used to obtain the amplification of very small magnitude signals. So basically what is the task here? The task here is to amplify very small magnitude signals. Okay, to amplify very small magnitude signals. Okay, so basically we are studying about DC amplifiers, and the job here is to amplify the signals which are coming from those kind of transducers or sensors uh, which are having very small magnitude, and they contain both DC as well as AC components. Okay, so and they are, it means that they are very slowly varying with time. Okay, and such a signal is called to have, is said to have both DC and AC components in it. Okay, that is one thing, but the main thing that poses the problem is that the magnitude of these signals are very small. Okay, the magnitude is very small, and because of this it becomes very hard to design amplifiers, okay, which can be used to directly amplify these. Okay, we can think of constructing or designing some very good amplifiers having very high gain, so that those amplifiers can be used directly to amplify these small signals, small magnitude signals. Okay, that can be done, but that is a costly affair. So and hence there are some other good alternatives available. Okay, so one of them is a chopper stabilized DC amplifier. Okay, let us see. As far as chopper stabilized DC amplifiers are considered, they give better stability, higher gain, and better gain versus frequency characteristic, means bandwidth. Okay, so what is the concept here? The concept here, the principle here is to we are having a DC signal as the input, right, and the task is to amplify that particular DC signal. So this DC signal converted into AC signal first. This DC signal is converted into AC signal, and that is done with the help of a chopper. Okay, chopper will convert that DC into AC signal, and then that AC version of the DC signal will be amplified in an AC amplifier, right, and after amplification the amplified AC signal will be converted into DC format. Okay, so here we are actually transforming DC signal into AC signal with the help of a chopper, then amplifying that AC signal, and then transforming back that amplified AC signal to the DC format. Okay, so this is the basic principle behind this chopper stabilized DC amplifiers. Okay, so look at here. Suppose this is the input signal. Okay, this is the input signal Vi, and chopper can be a simple switch. Okay, which will just close and open, close, open, close, open, alternately. So what happens when it is closed? The signal passes. Okay, and if this is the input signal Vi, this one, and this is the output signal V0, this one. Okay, so when the switch is closed, the signal will pass, and for a certain duration of time you will get for that small duration of time you will get the signal. Okay, now after some small duration of time the switch goes off. When it is off, the signal cannot pass. Okay, and you will get a zero signal here. Again, when it is on, you get the signal value. When it is off, again you don't get the signal, zero. Okay, so basically if this is the input signal, okay, so and this is the output signal, and when you compare these two, so we can very easily say that okay, this is a kind of chopped version of this signal, because the envelope is same. Okay, the envelope that it is following is same as that of this one. Okay, the only difference is that this in this envelope, okay, the signals are present only for some duration of time. For other duration of time, the signal is not there. This is simply not here. This is zero. Okay, and again for a small duration of time, the signal is present. Again for the next small duration of time, the signal is not present. Okay, so this happens because of the opening and closing of the switch. Okay, so we try to chop the signal in this fashion, and then this chopped signal should be amplified with the help of an AC amplifier. this should be amplified with the help of an AC amplifier. Okay, and after AC amplification it should be again converted back, DC conversion. Okay, DC conversion, it should be converted back into its DC format, that was the original format, and you will get, after this transformation, you will get the DC signal which is amplified version of the input signal which was a DC signal, that is Vi. Okay, so this is the basic principle behind this chopper stabilized DC amplifier. Okay, so let us see how does this work. So let's some points, some types of signals that need amplifying can be so small that an incredibly high gain is required. Okay, and basically these signals are coming from the those transducers or sensors whose output are actually very small in magnitude. Okay, they are in the range of some milli volts. Okay, and amplifying a millivolt signal is a big task. Okay, and but very high gain DC amplifiers are much harder to build with the low offset and 1/f noise. This is actually pink noise. Okay, and reasonable stability and bandwidth. It is there. We can build DC amplifiers that will provide us very high gain, but the point is that they are pretty hard to build, since just building is not enough. It should perform also. It should perform in the sense that it should have low offset. It should not amplify the noise part. Okay, it should provide us the proper stability factor, and it should have a proper bandwidth also. Okay, and satisfying all these parameters for a DC amplifier is a tough task. Okay, so and it's much easier to build an AC amplifier instead. Chopper circuit is used to break up the input signal so that it can be processed as if it were an AC signal. Okay, first stage is to chop the signal, so it will convert, the chopping will convert DC into AC part. Okay, and then amplify the AC, the chopped signal. Okay, and then integrated back to a DC signal at the output, then convert that amplified AC signal back to the DC format. Okay, so and we know that we know the circuit which is used for converting AC into DC. हाँ भैया. Okay, and we know about the circuit which is used to convert AC into DC. So recall from basic electronics that it is nothing but a rectifier circuit. So rectifiers are used for converting AC into DC, and chopper circuit will be used for converting DC into AC. Okay, and this particular circuit is actually useful, very useful in dealing with the drift. Okay, drift. The pulses obtained are amplified by an AC amplifier and back to obtain the DC amplified signal. Okay, this is the thing, right? And chopper can be a vibrating reed or a motor driven switch or an electronic switch. So basically it will be a switch, and the switch can be a mechanical switch or an electronic switch. Okay, so let's see one such amplifier, and this is called as a ring bridge modulator. Okay, right. So let's see the operation of this particular circuit. So look at here, it is called a ring bridge modulator because of the presence of this ring structure here. And this ring structure contains 4 diodes, D1, D2, D3 and D4. okay, and it reminds of something. Okay, it reminds us of the ring or bridge rectifier. Okay, but look, okay, but coming back to here, so this is the ring of diodes, and here we are having one, the first transformer TR1, and this is the second transformer TR2, and this is the AC amplifier. So it means that at the input of this, the AC signals will be fed. And where is the input signal? Okay, this is the input signal that is coming at these terminals, at these port. Okay, and this is the actually this is the DC signal. Okay, this is the DC signal which needs to be amplified. Okay, which needs to be amplified. All right, and there would be one modulating AC signal, okay, or also called as a reference signal. Okay, so if it is an AC signal, it means that it will change the polarity, it will change its polarity. So sometimes this will be positive, this will be negative, and at other times this will be negative and this will be positive, and it will continue like this. Okay, and this is a modulating signal which will be used for to modulate the input DC signal. Okay, so this is the input signal that we want to modify, and this is the DC signal, and this is the modulating signal that will be used to modify or modulate the DC signal into AC signal. Okay, so let us see how does this operate. Okay, so let's assume that the modulating signal is giving us this polarity for some duration of time. Okay, just let me start with this one. Positive. Okay, let's go continue with this. If this is positive, this is negative for 1/2 duration of the time period for this AC signal. Okay, and this will make this positive, this negative, this transformer, because this is a transformer. Okay, and with this positive and negative polarity, which diodes will be conducting? Look at here, D4 will be conducting and D3 will be conducting. Okay, what about D1 and D2? D1 and D2 will be not conducting. So it means that for this signal to pass, this path is not available, this path is blocked. Okay, and these two are conducting, these two are forward biased. Okay, so this path would be available. So for this particular polarity, the signal will flow through this branch, through A, through D4, through B, through D3, through C, and then back to this here. So this will be the path followed by this signal right now. Okay, now at the same time, when this thing is occurring here, the input signal is fed, the DC signal is fed here, right from these terminals. It enters here through R1 and goes to this second transistor TR2. Okay, now it will follow either P1 or P2 path. It will follow either the first primary P1 or the second primary P2, okay, of this transformer TR2, depending on the path that is available to it. Now right now, since this path is available, so the current will come and will follow this path, will come here, okay, and will come here through this branch, will come here and will go to the ground again, from the ground, and it will enter like this. So this path will be followed by I1, this path. Okay, so the loop is closed, the loop is complete. Okay, now you may be wondering that why is it coming from D3, why D3, why not from D4? Now it depends on the strength of the signal. Okay, if the signal is stronger, then it will follow this path. If the signal is weaker, then this current, then it will follow this path. So it doesn't matter. The point is that it will enter through R1 and it will pass through P1, and then via these paths it will go to the ground here and will form the closed path, and then it will continue like this. Okay, this is for the since this is an AC signal, so this will occur when this AC signal is positive, is in the one half, the positive half of the cycle. Now when this reverses its polarity, okay, these polarities will reverse. Okay, let me draw here. So for this polarity, this one, this will become negative, this will become positive, negative, positive. They will become forward biased, they will become reverse biased. So D2, D1 are available, right? And D4, D3 are not available, they are open circuit. So what will happen to I, input current? It will come here. Now in this case, since P1 path is not available because these are open circuited, so now it will follow this P2 path. Okay, so it will follow this branch, this will come from here and it will follow these branches and will come here and will go to the ground via this, and then it will again enter via this terminal. So in this way the loop is complete. Okay, and this the reversing of polarity will continue since this is an AC signal. Okay, so it shows us that for one half P1 path is available. Okay, and accordingly it will sample the signal at the secondary of transformer to TR2, and for the other half this path is available, so accordingly the signal will be sampled with the negative polarity at secondary of transformer TR2. Okay, so the polarities are changing, right? And you will get the chopped signal version of the input signal right here at the input of this AC amplifier. Okay, so here you will get, or here also you can say that at the secondary of transformer TR2, the chopped signal is available, and this is fed at the input of this AC amplifier, and you will get the output signal which is actually AC, but the amplified version of the input chopped signal. Okay, now after amplification of this AC signal, we need to convert that amplified version again back to DC format, because we are actually dealing with the DC signal. Okay, so we want to obtain the amplified version of this DC signal. So again a transformation from AC to DC needs to be done, and this is done with the help of rectifier. So there should be one rectifier here which will convert this AC signal into the DC signal, and then you will get the amplified DC version of the signal for this input signal, which was actually small magnitude DC signal. Okay, so in this way this particular circuit will work. All right. This operation is explained here in these points. Okay, and but I have already explained the operation, so we can go to the next topic. Look at here, this is again basically a chopper shown here. The chopper can be made more simple. It can be made with the help of a single transistor, a single transistor chopper, where only one transistor is used here, this one, and this is the input signal, which is actually DC signal, which needs to be chopped. Okay, and here you will get at V0 you will get the chopped DC signal. Okay, and remember I told you that we need a simple switch. A simple switching mechanism can perform this chopping operation. Just we need to cut the signal, right? Nothing else. So it uses a low resistance and high resistance path of transistor when cutoff and saturation. Okay, so the transistor will enter into cutoff and saturation alternately. Okay, so either it will be short or open circuit. Okay, depending on the signal that is fed into it, depending on its biasing conditions. Okay, and for that thing, one square signal is used here to drive this transistor into cutoff and saturation region. Okay, so let's say when for one half of the signal, the this transistor is in saturation. When it is in saturation, this path will be short circuit. Okay, this path will be short circuit, right? And input signal will appear at the output completely. Sorry, when this is short circuit, the output signal will be the output voltage across this short circuited path, which is actually, and we know that the short circuit path voltage drop is 0, so you will get a 0 here. Okay, now when this is in cutoff, this becomes open circuit, so this does not conduct, this becomes open circuited. Okay, so whatever voltage that appears at the input of at the input side, that is Vi, appears at the output, that is V0. Okay, so for when the, so in this way it operates. Okay, so when it is in saturation, the output voltage becomes 0, and when it is in cutoff, the output voltage becomes equal to input voltage, and this goes on repeating. So this is a pretty simple circuit which can be used for performing simple chopping operation. Okay, so for this, a square wave signal is applied to drive the transistor into cutoff and saturation alternately, and this process goes on to continue. Okay. Okay, right, and we can have chopper. We can have a chopper again made with the two transistor. So here this T1 is the first transistor and T2 is the second transistor which is used here. Okay, look at here, and this is the input signal, which is the DC signal, and this is output where chopped output signal will be available, and this is the input signal that will drive the transistors into saturation and cutoff. Okay, so again square wave modulating signal is applied to two transistor switches which are alternately driven into cutoff and saturation. Okay, so what will happen that with the application of this square wave signal, okay, the transistors will go into saturation or cutoff, and by the same process that we had seen here. Okay, when in saturation they will short circuit, they will behave like short circuit, and when in cutoff they will behave like open circuit, and accordingly the signal will appear at the primary of this transformer. Okay, primary of this transformer, and you will get the signal at the secondary of this transformer. That will be the chopped version of this input signal Vi. Okay, so I leave this operation I leave this thing to you. So you try to describe here, describe the operation of this two transistor chopper circuit in detail in your language. Okay, try to describe this operation in your language and describe in detail that what happens, which transistor is going to saturation or cutoff, and how is the signal appearing at the primary and at the secondary. So try to make it with the help with some signals representation at the input side and at the output side, and try to go into some more depth, some more detail, and then you will understand the operation completely. Okay, so but to wrap up, this is the two transistor chopper circuit. Okay, and this was the one transistor chopper circuit, single transistor chopper circuit, and before that we had seen the ring bridge modulator, which also chopped the signal at the same time, since we had conducted the AC amplifier. So at the same time here also we can connect one AC amplifier here. Okay, we can show one AC amplifier at the output part here or here, and at the output of AC amplifier the AC version will appear, and again you can connect one rectifier circuit that will convert back the AC amplified signal into the DC signal, and that DC signal will be the amplified version of this input DC signal Vi. Okay, so that will complete the circuit as a DC amplifier, a single transistor chopper based DC amplifier, or we can also call in this case a two transistor chopper based DC amplifier. Just we need to connect one AC amplifier here and one rectifier here. Okay, okay, then we will proceed from here. We will resume from here in the next class.